Okay, so this is the internal organization of computers. So for the computer here, you can see here there are three main parts, okay, that can be divided for every computer. Okay, so this main part here, okay, the computer should have, okay, or must have a CPU. One of the part that computer should have is CPU. Okay, so this CPU, and then memory as well as an input output. Okay, so for the CPU, okay, so this one here, this CPU is stand for Central Processing Unit. Okay, so this is the brain of the computer. Okay, later in the next few slides, we will learn about the this CPU more details. Okay, then we have a memory. So this memory can be divided into two types of memory, as I mentioned yesterday. Okay, there is a volatile memory and non-volatile memory. Okay, so example of memory here, such as a RAM and ROM. Okay, this is where you're going to store your data. And last but not least is your input-output devices lah. Okay, for the input devices, we have a keyboard, mouse, or sensors, or you can have a switches. Okay, while for the output, you can such as a LCD, printers, monitors, bulbs, lamps, LED, and etc. Okay, so for the embedded system, also have the same structure but at a small size. Okay, so embedded system also have the CPU, must have the CPU, memory, and input-output. Okay, so this is the internal organization of computers. Now we're going to look more details on the CPU parts, memory parts, and input-output parts. Okay, so for the CPU, okay, so this CPU used to control the operation of the computer and perform its data processing function. Okay, so this CPU often simply referred to as a processor. Okay, so inside of this processor, you will do the data processing, and at the same time, the CPU will execute the information that are stored in the memory. Okay, so in order to connect this CPU, okay, with a memory and input output, so we need to we need to have a buses lah in order to do the communication between the CPU with the memory and CPU with the uh, input output. Okay, so these buses, yeah, okay, we have three buses, which is the address bus, data bus, and control bus. Okay, the size of these buses depending on the CPU that you're going to use. Okay, so later in the next few slides, we'll look more detail on what this address bus do, what are the data bus do, and the control bus, the function of the control bus. So in this CPU, okay, so this CPU is actually made of from three main units. Okay, so inside of the CPU, you have another three main units called as a ALU, okay, arithmetic logic unit, and then you have a control unit as well as you have a register. So this is the overview of your CPU. Okay, so you have the ALU kat sini, and then you have a registers, and you have the control unit. So this register here used to store the data temporarily. Okay, so every time you're going to process the data, you will store that data to this register. Okay, you take the data, you retrieve the data from the memory, okay, which is outside the CPU, and put it to your register, okay, and store it temporarily. Okay, for the ALU, okay, so this ALU used to perform all arithmetic operations such as addition, subtraction, division, and multiplication. And at the same time, this ALU also used to perform a logical function such as AND or exclusive NOR, and etc. Okay, then you have the unit kawalan, which is your control unit. So this control unit used to control and synchronize overall operation of the computer and embedded system. I don't know why. Okay, so I think I need to restart my Microsoft PowerPoint because now it's not responding. Okay, can I have 5 minutes? Okay, 2 or 3 minutes.
Okey, doktor.
Boleh ya? Sekejap eh. Okay, so for those who just joining the class, okay, please scan the QR code for today's attendance. Okay, so where are we? Okay, here. So we are in the CPU. All right, so actually, okay, there are two types of CPU. Okay, one we call it as a microprocessor, and the other one we call it as a microcontroller. Okay, so microprocessor and microcontroller is two different things, but this microprocessor and microcontroller is actually your CPU. Okay, your central processing unit. Okay, then okay, so since the computer need to have three main parts, which is first is CPU, then memory. Now you're going to see what the memory is. Okay, so memory store the binary information needed by CPU. So actually, this memory here use to store the data. Okay, you're going to add as a data storage. Okay, there are two types of memory. Okay, one is a volatile memory and the other one is a non-volatile memory. Okay, so here you can see here you have a ROM and RAM. Okay, so ROM, which is a read-only memory, is a non-volatile memory. So I assume that all of you already know what is the non-volatile memory and what is the volatile memory is. Okay, so this non-volatile memory content is retained even without the power supply. Okay, so in embedded system, okay, so this ROM used to store application program and test routine. So inside of the system, you will store all the application program inside of this ROM here. Okay, so this content can be set by fixing it during manufacturing or burning it using a programming device. So there are common type of ROMs such as a MROM, which is mass ROM, and then you have a PROM, okay, programmable ROM, EPROM, erasable PROM, and flash memory. So the erasable type can only be rewritten a fixed number of times. So this is the ROM types lah. Okay, you have an MROM, PROM, EPROM, and flash memory. Okay, next we move to RAM, okay, which is a random access memory. Okay, for the random access memory, it's actually a volatile memory. Okay, whatever you store inside of this memory will be lost after you shut off or shut down the power supply. Okay, so this RAM is used to store temporary data. Okay, so only a temporary data will be stored to your RAM. So in embedded system, very little RAM is required. Some systems don't even have a RAM at all. But for Atmega 32, we have a RAM. Okay, the size of the RAM, it depends on the chip that you are buying to you. Okay, so that is for the memory. Okay, so this one here, okay. Actually, we have a few RAM. We have a DRAM, SRAM, DDRRAM, and that one you can you already learned in the digital electronics. Okay, then we are going to see the buses here. Okay, so these buses here used to communicate between the CPU with memory, CPU with I/O, and I/O with memory. So this buses is actually the communication pathway. Okay, so there are three types of buses. Okay, we have the address bus, data bus, and control bus. Okay, you can see from these buses here, you can see the arrow. Okay, some of them is pointed out from CPU. Okay, and some of them is a bi-directional bus. Okay, so let's look at these buses here. So first we look at the control bus. Okay, so this is a control bus. Okay, so it is a bi-directional bus. Okay, so you can see this arrow here. It either can go in or go out. Okay, so that's why we call it as a bi-directional bus. Okay, so this control bus used to provide read or write signal to device indicate if the CPU is asking for information or sending an information. So this control bus actually will control the data. Either you're going to read the data or you're going to write the data. Okay, if you're going to read a data, then the data will come in from this data bus. Okay, from outside to the CPU. If the control bus says that, okay, we're going to write a data, means that you're going to send out a data from CPU to your memory or your I/O by using a data bus. Okay, so this is only for the control purpose. Either you're going to read or you're going to write. Okay, then we have a data bus. Okay, so this data bus also is a bi-directional bus, which is it is a two-way communication. Either you want to send in the data to your CPU or to send out the data from your CPU. Okay, so this data bus used to carry information in and out of the CPU. So all of the information from your input output or in your memory will be carried from using the data bus. Okay, so the more data buses available, the better the CPU, but more expensive. Okay, so to this, okay, what is the size of your computer? What is the n bit size of your computer to this? Can you tell me? What is the size of your computer? Is it a 16-bit, 32-bit, or 8-bit computer? Anyone?
32.
Oh,
32.
32. Is it 32?
Yes, there is 32 and 64, I think.
Okay. Nowadays it's a 64.
Yes,
Okay.
64.
So
Sorry.
so actually the 64-bit, okay, actually it indicates the size of your data bus. Okay, the 64-bit here is the size of your data bus. Okay. So a few years later, we have a 32-bit computer, and sometime maybe 10 years before we have a 16-bit, and 20 years before we have a 8-bit computer. Okay, so this bit here actually is the size of the data bus. Okay, so the processing power of computer is related to the size of the data buses. Okay, so 8-bit bus can send 1 byte a time, while 60-bit bus can send 2 byte data at a time, which is twice as fast lah. Contoh, okay, let's do an example here. Okay, you have a 16-bit data. Okay, you're going to send 32-bit data. Okay, so by using a 64-bit computer, you can send out this 32-bit data in one cycle. Okay, for the 32-bit computer also, you can send out this 32-bit data in 1 cycle. But if you're going to use the 60-bit data bus, okay, what happened here? Because the size of the data is 32-bit, so you need to divide it, this data here, okay, from 32, you need to divide it into 2 small chunks, which is 60-bit and 60-bit. So how many cycles that you got required in order to send out the 32-bit data by using a 60-bit computer? 2 cycles. Okay. If you're going to use the 8-bit data bus, what happened here? How many cycles? Okay, you need to divide it lah. 32 ni you divide it by 8. Okay, 8-bit chunk, 8-bit data, 8-bit data, and 8-bit data. So how many cycles you require to send out this 32-bit data? You need 4 cycles. Okay, so this data bus is actually important lah in order to determine either your CPU is faster or not. Okay, but of course lah. Okay, the better the CPU or the more the data bus available, the more expensive your expensive computers, right? So this is for the data bus, and then last one here, address bus. So for the address bus, as we can see here, this is only unidirectional bus. Unidirectional bus. Okay, you can see here. Okay, the arrow is only coming out from the CPU. Okay, so that's why we call it as a unidirectional bus. Okay, you have a one directional. Okay, this address bus actually used to identify the device and memory that are connected to CPU. Okay, so actually the address bus is used to identify the device that are connected to your memory or to your input-output and CPU. Okay, for example lah. Okay, in order to send a letter of postcode to someone, okay, you need to have your friend's address house. Is it? Okay, without your friend address house, so you cannot send the letter or postcode to your friend. Okay, similar to this one lah. So the address bus actually contain the address of the device and memory that are connected to CPU. Okay, so for a device to be recognized by a CPU, it must be assigned by unique address. So, for example, you have what you call here, a printer. So this printer here should have a unique address. Okay, and then if you're going to connect your computer with monitor, so this monitor also you need to have a special or unique address. Okay, the address cannot the address of printer and monitor cannot same lah. Okay, cannot similar to one from one to another. It must be different. Okay, so the CPU will put the address, which is of course lah in binary, on the address bus, and the decoding circuit find the device. Okay, since you know that, okay, let's say lah the address of the printers is, let's say, is 0001. So now the CPU going to use the printer, so it will put this address to the address bus. Okay, and then what happened here? The decoding circuitry will find the printer, and once it find the printer, then it will print out whatever the CPU, whatever the data that CPU going to send out. Okay, so the more address bus available, the larger the number of devices that can be addressed. Okay, so the size of the address bus will determine how many devices that you're going to connect to your CPU. Okay, any question up until here? Ada soalan tak? Okay, if no question, then we go to the next slide. Okay, so now we're going to see the CPU. Okay, as I mentioned earlier, we have a 2 CPU. All right. One is a microprocessor and the other one is microcontroller. Now we are going to see what are the difference between microprocessor and microcontroller. Okay, so the microprocessor is a single integrated circuit that accept and execute coded instruction, which is in the machine code or machine language for the purpose of manipulating data and controlling the associated circuitry such as RAM, ROM, I/O in a digital system. So this is the microprocessor in a single IC, okay, in the single integrated circuit. Okay, so microprocessor by itself is completely useless. Why? Why microprocessor by itself is completely useless? Kenapa? Why? Can anyone tell me why the microprocessor by itself is useless? Okay, so as okay, Chopna thinks that could it just a brain. Okay, so recall back. Okay, for the computer system, what are the three main things that you required in order to make a one computer system? Okay, you need to have a CPU.
Input output.
Okay, I/O as well
Memory.
as memory. Okay, now you only have the CPU. Okay, you doesn't have the I/O and you doesn't have the memory. So that's why it's a complete useless. Okay, because the microprocessor itself is only a CPU. It's only the brain. Okay, in order to make a one complete system, you need to connect it to the memory. Okay, so this is your memory. The green color here is your memory. And as well as other peripherals, which is the I/O peripherals. Okay, so that's why you need to have another chip lah. Another chip for the ROM, another chip for the RAM, and another chip for your input output and connect it to your CPU so that it become one computer system. Okay, so that is a microprocessor. Why? For the microcontroller, okay, it's also a single integrated circuit. Okay, this sama juga. Similar to micro P, it also in the single integrated circuit. Okay, that accept and execute coded instruction for the purpose of manipulating data and controlling the digital system similar to micro P. But okay, the difference between micro P and micro C is that the micro C contains RAM, ROM, and I/O in that single IC package. Means that okay, every time you buy the microcontroller, okay, so inside of this microcontroller, it already have the CPU and the other ROM and RAM as well as your I/O peripherals. Okay, so this one is it is a one complete computer system lah. Okay, so it will allow miniaturization of a single application because the required associated circuit is contained within the IC of microcontroller. Okay, so what happened here? So this is your micro C. Okay, so inside of your micro C, you already have the CPU. Okay, so this is your micro C lah. So this is your micro C. So inside of the micro C, you already have a CPU, and then you have the memory as well as the I/O peripherals. Okay, so that is the difference between microprocessor and microcontroller. Any question up until here? Is it too fast?
It's okay, Doctor.
Okay, so SM someone asking here, which component is responsible for decrypting the binary? Okay, what component? They are responsible to create the binary.
Like Doctor, the CPU actually gives a signal, binary signal to other components, right?
Yeah, correct. So actually inside the CPU, all the value, the data information is in binary numbers.
So where this information, this binary signals coming from? Like who generating the binary signals?
Okay, so
Is it the CPU or just a memory or some inputs? Like I just want to know.
okay, it depends. Okay, if you're going to read a data, okay, so the binary number is coming from your inputs. Okay.
Is it power? Is it power?
No, it is either your switches, your sensors, or your analog to digital converter.
Understood, Doctor.
Okay. So any other questions? Okay, if no question, then we go to the next slides. Okay, then we are going to see what is other differences between microprocessor and microcontroller. Okay, so let's look at the microprocessor first. Okay, so this microprocessor is a chip that contains only the processor. Okay, as I mentioned earlier, it only have a CPU, doesn't have the memory and input output. Okay, but while microcontroller, it is a chip that contains all the components of the computer, which is you have the CPU, you have the memory, and then you have the input output inside of the chips. Okay, so next, the microprocessor need another chip to make a working system. Okay, to make a one computer system, okay, for the microprocessor, you need to add another chip such as a ROM, RAM, as well as your I/O peripherals. Okay, and this one, microprocessor is more flexible, and this one less flexible. Why this one more flexible and this one less flexible? Okay, because the microprocessor, okay, let's say lah, if you, okay, you go, okay, you buy one microprocessor, and then you're going to have the input output, your GPIO. Okay, you're going to connect 64 sensor to your system. So what happened here is you buy a 64 GP input output chip and integrate with your CPU. But for this one here, okay, and before that, okay, so you already bought the 64 GPIO, okay, and then let's say lah, in the next assignment, you're going to expand this GPIO from 64 to 64, and then you're going to expand to 86, for example, input output that you're going to use for this project. So what happened here? So you already has a 64. So what happened here is you need to add another 32. Okay, sorry, not 32. Okay, so 86, 64. So you're going to add another 22 GPIO. Okay, so you just buy out the 22 input output peripheral chips and integrate with your microprocessor. So what happens for this one here, for the microcontroller, let's say lah, okay, at first you're going to buy the 64, okay, you're going to make use a 64 input output. Okay, so you buy a microcontroller, okay, an IC that consists of 64 IO. But later you're going to increase the number of this input output, okay, you're going to integrate more sensors to your system, okay, to your project, to 86 sensors. So what happened here, since this one only have a 64, okay, so what you're going to do is you no longer, okay, you cannot use this microcontroller anymore. Okay, you need to buy a new one. Okay, so that that what we call by less flexibility. Okay. Okay, in order to support up to 86 input output, so you need to buy a new chip. But this one here, you only need to buy the input output in peripheral chips only. But this one you need to buy the whole system lah. Okay. Okay, next can have a very few I/O or many I/O devices using the same processor or chip. Okay, and then this one, okay, this is a similar to the more flexible lah. Okay, you can have more I/O or many I/O by using the same processor. Okay, and for the microcontroller, less component count in the system. Okay, because it is all of the RAM and I/O you need to put inside one chip, so you need to have it. It will have a less component count lah, and it is a less powerful compared to microprocessor. Okay, so that is the difference between microprocessor and microcontroller. Okay, now we are going to see on, okay, we already learned about the fundamental part. So now we are going to see on the programming part. Okay, so what happened in the process when you grow. So this is the thing that you're going to see in the next few slides. Okay, how to write a program, how to run a program, create the program, how to do the troubleshooting. Okay, so let's look at this software here. Okay, so to do a program, okay, you need a computer software. Okay, so this computer software is actually a computer program known as a software. So for example, okay, if you're going to do the word processing, okay, you need to have a Microsoft Word program. Okay, if you're going to do the what we call here image processing, so you need to have an Adobe Photoshop software. Okay, so that is a computer software. Okay, while for the program, a program is actually a sequence of instructions that perform a task. Okay, so this is example of the program. Okay, so this is example of a program, which is inside of this program you have a sequence of instructions that perform a few tasks. Okay, so why for the instruction, okay, so this instruction is actually the simplest operation performed by the processor. Okay, so think of it as a note coming from a musical instrument. So this is a program. Okay, and then so this is the instruction. Okay, you have two instructions here, ADD R1 R2 and ADD R28 R28. So in the next module, you will learn about this instruction. Okay, so and last but not least is here is how, okay, in the next few slides, you're going to learn how the computer works. Okay, so this is the step taken, okay, on how the computer will work. Okay, first you need to fetch an instruction from a memory, and then after that, after you fetch the instruction from the memory, you decode that instruction. Once you already decoded the instruction, then you execute the instruction. So this one we call it as a fetch and execute cycle. Okay, so this process will keep repeating until, okay, until you finish all of these instruction here. Okay, so the fetch and the execute cycle will keep repeating from the top of your program until the last of this instruction. Okay, so regarding the language that you're going to use, okay, so let's look at this figure here. Okay, as you can see, the low level here is your hardware. and then followed by the machine language, and then after that, after the machine language, you have the assembly language, and on the top of this pyramid here, okay, is the high level language such as a Fortran, C programming, Pascal, or you have a Java, you have the Python. Okay, so let's look at this machine language first. Okay, so the machine language is the lowest level programming machine. Okay, so the machine language is the lowest programming. Okay, as you can see here, okay, the location of the machine language is near to your hardware. Okay, so actually it is a set of instructions that execute directly by CPU. Okay, while easily understood by the computer, machine language are almost impossible for human to use because they consist of entirely of numbers. Okay, so this is an example of the machine language. If you can see here, okay, it is contained of numbers. Okay, so this is in hexadecimal lah. Okay, because we some of the assembler, okay, going to simplify the machine language, so it use the hexadecimal. Okay, most of the time, okay, we can convert this to binary numbers. Okay, so this is the machine language, and if you can see, okay, here, okay, at the right column here, okay, so this is the assembly language. Okay, so by looking at this number, you cannot tell what this number represent to. Okay, but by looking at the assembly language, you know that, oh, now we're going to push the data to your stack pointer. And then for this one, MOV, you know that, okay, we're going to move a data from one memory to another memory. But for the machine language, you cannot tell what this 89E5 do. Okay, so this is only understood by the hardware, by the CPU. Okay, then we have the assembly language. Okay, so the assembly language is a low-level programming language for a computer. So assembly language use a mnemonic representation, okay, to represent each low-level machine operation. Okay, for example, every time you see the MUL instruction, so you know that it stands for multiply. If you come across ADD, you know that that one stand for addition. As if you see the SUB, you know that this one is going to do a subtraction, and MOV, you're going to move a data. Okay, LDI, you're going to load a immediate value to a register. Okay, later we will see on this instruction of assembly language. So assembly language is converted into executed machine code by a utility program referred to as assembler. So the assembler, what the assembler do is, okay, it will decode this instruction here to the machine code. Okay, so assembler can be of two types. Okay, there are two types of assembler. One is cross assembler, the other one is native assembler. Okay, for the cross assembler, okay, runs on one computer and generate machine instruction that will executed by another computer that has different instruction set. Means that, okay, for the cross assembler, okay, you write down your assembly language on computer A, and then you generate that machine instruction, okay, the machine's code, and then that machine code that generated, you run to the computer B. So that is a cross assembler. While for the native assembler, okay, you're going to run and generate instruction, okay, on the same computer. Means that you do the program or assembly program in computer A, and at the same time you run it on the computer A as well. Okay, so that is a native assembly. Okay, so what are the drawback of assembly program? Okay, so the drawback here is depending on the hardware organization. Okay, you need to know the hardware organization. Means that you need to know how, for example lah, for Atmega 32 IC. Okay, you need to know the hardware in organization. Okay, how many input output port available? Okay, what is the input output pin out? Okay, and where you're going to put the switch, the reset button, where is the pin that used to trigger the interrupt, and so on. Okay, so you need to know the hardware organization. Okay, sometimes it is difficult to understand long program and low programmer productivity. Okay, because you have a very long program here. Okay, sometimes it is difficult to understand compared to C programming. Okay, so that is the drawback of the assembly language. Okay, and last but not least, the high-level language lah. So this high-level language is a programming language such as C program, Pascal. You have a Fortran, and then you have a Java, Python. Okay, so this program here enables a programmer to write programs that are more or less independent of a particular type of computer. Okay, so this program here easy to use, easy to understand. Okay, you no need to know the organization's hardware of the hardware organization. Okay, you just use them. Okay, no need to know the specific hardware organization compared to assembly language. Okay, so now we're going to see the instruction cycle, okay, which is consists of the fetch and execute. Okay, so this instruction cycle is very what we call here important lah, in order to fetch the instruction, and after that, after you fetch the instruction, and then after that you going in the next cycle you're going to execute that instruction. So the processor executes instruction one by one according to the sequence found in a memory. Okay, so similar to this one here. Okay, so let's say lah, this is your instruction. Okay, so what happened here is, okay, the CPU will fetch this instruction one by one from top to the bottom. Okay, so everything is controlled by the control unit in the CPU. So everything will be controlled by the control unit, the C unit inside of the CPU. Okay, to execute an instruction, what happened here is the processor must fetch it from the memory. So means that before you execute that instruction, you need to fetch that instruction from the memory. And once you fetch the instruction from the memory, then after that you can execute that. Okay, before that, okay, this is just a quick overview, because this one here you will learn in the next module. Okay, for Atmega 32, we have 3 type of memory. Okay, kita ada 3 memory. First, we call it as a program memory. Okay, then we have a data memory. And the third one, we have a double EEPROM memory. Okay, but for this class here, we only focus on these 2 memory here. Okay, so the program memory, okay, is the memory that will store all the instruction. Okay, means that every time you write down the program, all the program will be stored inside in this program memory. While for the data memory, okay, so every time you're going to execute the instruction inside of this program memory, so all the instruction, okay, will be stored. Okay, all the data from this instruction will be stored to your data memory. Okay, so there is two different things. One, store the program. Okay. The other one, okay, used to store the data after you do the data processing. Okay, which is after you execute the instruction. All the data okay, all the data after you execute the instruction will be stored to the data memory. Okay, so the complete step the processor takes to execute one instruction in the instruction cycle or the fetch execute cycle. Okay, so one complete step from fetch the instruction and after that execute the instruction, we call it as a one instruction cycle, or sometimes we call it as a fetch execute cycle. Okay, so this is the what we call here, this is a program. Okay, if you can see here, inside of this program here, you have a lot of instruction. Okay, so what happened here, the CPU will fetch lines by line, okay, from top to bottom, okay, line by line, and then after that, it will execute. Okay, so this program actually, okay, all this program here will be stored to the program memory. Okay, after you execute this program here, so what happened after each of this line here? Okay, so the data, what happened to each of this line here will be stored to your data memory. Okay, later we will see how the program work, how the fetch and execute cycle works. So this is the instruction cycle details. Okay, so what happened here is on the program start. Okay, every time you start your program, so what happened? First you're going to load the program counter with the address of the first instruction. Okay, so you will come. Okay, you will always come across with this PC. Okay, the PC stand for program counter. So this program counter used to store the address of your instruction that you're going to execute. Okay, so what happened here on the program start? Okay, you load the program counter with the address of the first instruction. Okay, so each of these instruction here will be stored in the program memory, which is all of the instruction will have the address. Okay, so what happened? The CPU will take this address and put it to your program counter. Okay, so next for the fetch phase, okay, untuk fasa fetch, what happen is, okay, read the instruction and put it into the instruction register. So what happen here is, okay, the CPU will take the instruction and put it to your instruction register, and control unit decode the instruction. So the control unit will decode the instruction, what the CPU going to do, okay, and update the PC for the next instruction. Once the fetch is complete, what happened here is the program counter will take the second, okay, the next address of the instruction. Okay, then after that, the execute phase is begin. Okay, so what happened here? Find the data required by instruction, depending on the instruction lah. Okay, depending on the instruction, what the instruction going to do, and perform the required operation and store the result to the data memory. Okay, and this step will be repeat from this fetch phase, and it will keep repeating until the last of the instruction. Okay, so this is a instruction cycle examples. Okay, first you fetch the instruction pointed by the PC, increment the PC so that the PC will point to the next instruction. Okay, then after that it will decode the instruction. After it decode the instruction, then the instruction will execute, and the process will keep repeating. Okay, so this is what happened inside of the computer system. Okay, so this is your program counter. So program counter will take the address of the instruction. Okay, and then it will put to your instruction register. Once the instruction is put to instruction register, what happens is the program counter will incremented by 1, and after that, the instruction will be executed. Okay, so let's look at this. Okay, I'm going to show you how the fetch and execute cycle works by using the AVR Studio. Okay, so we're going to use the AVR Studio for this course. Okay, I open the AVR Studio first. Okay, for those who not yet to sign the attendance, please do so by scan this QR code. Okay, someone asking that computer can be called a microcontroller. Okay, it depends. Okay, we not call it a microcontroller. So as I mentioned earlier, okay, we have a few type of computer. Okay, there is a servers, there is a desktop, and you have a laptop, and you have a embedded system. Okay, it depending on the what you're going to do with that computer, and that will okay. So actually, the computer itself have the CPU, which is you have the microcontroller, and then you have the ROM and RAM, as well as the input-output device. Okay, so this is the Atmega 32. Sorry, this is the Atmega Studio. Okay, so this is the software that we're going to use in this course. Okay, so I'm going to create a new project. Okay, so inside of this AVR Studio, okay, you can write by using the assembly language or C programming. Okay, so now I'm going to show you how to write in the assembly language. Okay, so I just click the assembler and put anything that I put the name here. Okay, I just put the fetch and execute. Okay, then I click OK. Okay, now here you're going to select the what we call here the chip that you're going to use. Okay, so in this course we're going to use the Atmega 32 chip. Okay, so I just write down Atmega 32, Atmega 32. Okay, and then press enter, and then you can see this is Atmega 32. Okay, actually we have a lot of chips here. Okay, you can see you have Atmega 32.4, Atmega 32.5, and 32.8, and all those things. Atmega 64 and banyak lagi lah. Okay, so this Atmega 32. Okay, so we choose the Atmega 32 because you will learn about it in this courses. Okay, so actually the hardware organization from one chip to another chip is varies depending on the size of that chip. Okay, you can see here. Okay, for Atmega 32, the program memory is 32 kilobyte. Okay, while the RAM size is 2 kilobyte and EEPROM is 1 kilobyte. Okay, so I just click OK. Okay, so this is where you're going to write your program. Okay, so I write down a few program here. So I put ORT. Okay, so this is the program that I write. Okay, so now we're going to, okay, so we're going to compile it, okay, to check whether it have a syntax error or not. So you just click the build and build solution. Okay, if the build is succeeded, so no error, so it, okay, you can see this message here. Okay, if there is error, so you need to do a troubleshoot lah. Okay, now we're going to, okay, someone's asking that all are 32 byte. What is the difference? Okay, so the difference is maybe, okay, some of them have a 40 input output, some of them have a 8 input output port, some of them have 16 input output port. Even though the size of program memory, the size of RAM and EEPROM are similar, but the number of input output port are different. Okay, now I'm going to start and debug and break. Okay, so this one set to simulator. Okay, so you can see here, so this is the okay, can you see here? All right, see this is your program counter. Okay, and this is the stack pointer, X register, Y register, Z register, your status register. All the register are actually inside of your data memory. And this is you have a okay, you have 32 or a total of 32 GPR. So this GPR also inside of your data memory. And this is your okay, for this memory here, you have a program flash, and you can select this one. Either you're going to select the program flash or IRAM. So I'm going to see for the IRAM. So IRAM actually is your RAM lah. Okay, so the RAM is located inside of your data memory as well. Okay, so by looking at this, okay, so now we're going to see the fetch and execute cycle. Okay, you can see the program counter now started at address 000. How you know that? Okay, so you look at this assembly. Okay, you see this yellow line here, yellow arrow. Okay, it show at address 000. So now the program counter point to this address. Okay, actually at this address, okay, which is inside of your program memory, you doesn't have any instruction. Okay, so at this address, it doesn't have any instruction. Okay, because this is too big. Okay, I just reduce the number lah, because this is 200 is too big, hard for us to see. Okay, I just put the 10 lah kat situ. Okay, I run again one more time. Okay, again, you see here the program counter point to address 00. You see this is address 00. Okay, and then this program here, okay, ORG OX10, what happened here is means that I'm going to origin, okay, I'm going to origin all these instructions here to be stored starting at address 10 inside of my program memory. Okay, so you can see at address 10, so this is address 10. Okay, you have the LDI, the first instruction. Okay, address 0011, you have the second instruction here. 0012, you have the third instruction, and 0013, you have the fourth instruction. Okay, so this one actually you can change lah. If you don't want to put here, okay, you don't want to origin at any addresses, okay, you just put something like this, okay, and then you run. So this one here, since you're not origin to any what we call here any location, so what happened? Okay, you see the starting at address 00, you store all this instruction. Okay, all this instruction is stored at starting at address 00 inside of your program memory. You see 0, 0, you have the LDI R60, the first instruction, 0, 1, the second instruction, 0, 2, the third instruction, and 0, 4, your fourth instruction. Okay, so I just put something like this. Okay, since this here, okay, now there is no instruction here. Okay, so the program counter started point to address 00. Okay, so since there is no instruction, so the fetch execute cycle will not started lah. Okay, so I press the F10. Okay, so now you see this yellow line. Okay, the yellow line here indicates this is the instruction that is currently fetched by your program counter. Okay, you see the program counter now point to address 10. Okay, why 10? Because, okay, you can see, okay, the address 10 is where you store the LDI R16OX17. Okay, your first instruction is stored at this address 10. That's why the program counter now point to this address because it was going to fetch the first instruction. Okay, so currently, if you can see from this registers here, okay, there is no value. Okay, because you not execute anything yet. Okay, you just only fetch the instruction, not execute anything. Okay, once this yellow line here go to the next instruction, then what happen? This instruction is executed. Okay, for example, yeah. Okay, now this yellow line go to next instruction. Okay, so you see the program counter now increase to 11, which is fetch this instruction here. What happened here now is this instruction already executed. Means that you're going to load this value 17 and put it to your R16. Okay, you see the card R16. Okay, your GPR R16, the value 17 is stored to this register. Okay, you see here 17 stored to this register. Okay, now you fetch the next instruction, which is load IR1710. Okay, the 0x here, this 0x means that this is this number here in hexadecimal. Okay, if you put the symbol 0x, 0x ataupun or $sign means that it is belong to hexadecimal number. Okay, so now program counter point to address 11. So program counter point to address 11. You see here inside of your program memory. Okay, so next you're going to execute. Okay, next you're going to fetch this instruction, and then after that execute it. Okay, we should load IR1710. Okay, once this yellow line here go to the next instruction, then after that the second instruction here will be executed. Okay, you see the card R17. Okay, this is R17. The value is still 0, okay? Okay, the value is still 0, means that it's not executed yet because now you just fetch the instruction. Okay, not executed yet. Okay, then after that, what happened here is when this line go to the next instruction, okay. So what happened? Now you execute the second instruction here. Okay, which is you put 10 to R17. Okay, so if you don't put any symbol in front of this number, so this value here belong to decimal number. Okay, so 10, if you convert to hexadecimal, the value will be 0A. So 0A you put to R17. Okay, now what happened here? You're going to fetch another instruction, which is your program counter point to the next address, which is the address 12. Okay, address 12 is where you store the next instruction. Okay, then after that you execute this instruction. What happened? F10. So what happened? Now you see ADD R16, R17. What happened here is R17 you add with R16 and put the result to R16. Okay, you have a 17 plus with 0A, and after that you put the result to R16. So now that's why the R16 now change from 17 to 21. Okay, and then the program counter will increment by 1. So in order to fetch the next instruction. So this is how the fetch and execute cycles work. Okay, you're going to fetch the instruction first. Okay, then when the program counter increment by 1, then after that you execute that instruction.
Doctor,
Yes, sir. Yes.
for adding to register, the R16 or R17 is the first.
Okay, so in this case here, R17 is your okay, so R16 is destination register, R17 is your location register. Okay, means you're going to add value from R17 and value from R16 and put the result to your R16.
So, Doctor, the columns on the right side columns, the very right side, they're representing my locations right now, that where
Yeah.
I'm at.
Yeah,
And
this one this okay, from here, okay, you can see, okay, you just to make it simple, okay, whatever on the left hand side, that is your destination destination. Okay, so just this one, okay, the right hand side here, just you're going to take a value from a certain location. Okay, never mind. We will go
Doctor?
more go more details on this instruction later in the next module.
Okay, I may have missed it, but the first line of code here, what is it for?
LDI.
No, the one before.
Okay, this one.
Yeah.
ORG. Okay,
Yeah.
the ORG means that you're going to origin your program. Where you're going to origin your program. Okay, if you put the ORG OX10 means that you're going to start your program. Okay, so this program will be stored at address 10 in program memory. Okay, if you put 100, okay, for example, I put 100 here. So this instruction here will be stored at address 100.
Okay, got it.
so,
Okay,
Doctor,
so
the 100 is the RAM memory, like the whole.
not RAM memory. It is in program memory.
Flash memory, maybe.
Program memory. Your flash memory. Okay,
So it works like it's a folder, and then inside I'm selecting the location. That's all about, right, Doctor?
yes, you can simply put something like that. It's the location where you put all the instruction that you're going to fetch. Okay, any other question?
Doctor,
Yeah.
for cycle counter, start from where when we debugging the program?
The cycle counter, what you means by the cycle counter?
I mean, start the value of cycle counter start from any value. Which value?
Cycle counter. You mean this cycle counter here? Is it?
Yes.
Okay, so the cycle counter actually, okay, let us run this one first. Okay. Okay, so this one actually, okay, the cycle counter means that it depending on the instruction itself, okay, and the speed of your processor. Okay, if you use the much higher speed processor, then the cycle counter will be smaller lah. So this one you will learn in module timer programming, if not mistaken, for the cycle counter. Okay, so this cycle counter will depending on the instruction. Okay, what instruction that you're going to use, because every instruction have different cycle counter. Okay, for example, for the LDI here, we have one cycle counter. Okay, for ADD, okay, ADD, what about ADD? How many cycle counter do we have for ADD? Let me check first. Okay, if we run here, F10. Okay, so this one is 256, 257, and LDD is also one cycle. Okay, because there are some such a JMP instruction, if not mistaken, it is a 3 cycle counter. Okay, later we will see more detail on that part.
Thank you, Doctor.
Okay, if no question, then I think that is for the module 1. Module 1. Okay, that is for the module 1. Okay, now we go. We take 5-minute breaks. Okay, and then we will continue with module 2. Is it okay with you?
Okay, Doctor.
Okay. So we stop. We take 5-minute break, and after that we continue with module 2. Okay. Okay, so let's look at the architecture and organization definition. Okay, we're going to see what are the definition of the architecture and organization. All right, so architecture is actually how a computer system is designed and what technology it is compatible with. Okay, so every time you're going to design a certain computer system, so that one is belong to architecture. Okay, so the attribute of a system are visible to programmer. Okay, means that all the attributes, all the number of input, output, the peripherals, the RAM size, ROM size, okay, how many register available in that system are visible to programmer. So programmer need to know in order to do program. Okay, so this attribute have a direct impact on the logical execution of a program, such as the instruction set. What are the instruction set that we're going to use? Okay, number of bit used for the data representation. Is it a 8-bit computer or 16-bit computer? Is it a 32-bit data? Okay, and what are the I/O mechanism and addressing technique that required in order to to get or to move a certain data. Okay, so there are two types of computer architectures. Okay, this computer architecture can be divided into two types. One is we call it as a von Neumann architecture. The other one we call it as a Harvard architecture. So a von Neumann architecture is a computer architecture with a physically single storage and signal pathway for instruction and data. Means that, okay, by using the von Neumann architecture, all the memory or okay will share the same buses. Okay, they will share the same signal pathway. While for the Harvard architecture, it's a computer architecture with a physically separate storage and signal pathway for instruction and data. Okay, means that it has different buses in order to to communicate between your program memory and data memory. Okay, you have the separate buses, okay, and a separate storage. So this is the von Neumann architecture. Okay, if you can see it, you have a CPU and you have the code memory. So this code memory is where you put all the program inside it. Okay, where you save the program inside it, and this is the data memory. Okay, so in this von Neumann architecture, you can see all the what you call it, the buses are shared among code memory and data memory. Okay, so the computer has a single storage system, memory for storing data as well as a program to be executed. Okay, because you don't have what we call the separate. So this processor need 2 clock cycles to complete an instruction. Okay, so to complete a certain instruction, you need 2 clock cycle lah. Okay, for example, previously, okay, for the ADD instruction, actually it can be done in 1 clock cycle, but by using the von Neumann architecture, you require 2 clock cycles. Okay, because why? Because you share the same buses kat situ. Okay, so pipelining, okay, or multitasking, the instruction is not possible with this architecture. Okay, so in the first clock cycle, the processor will get the instruction from the program from memory and decode it. Can you give me 2 minutes? Okay, so you need to recall back the fetch and execute cycle that we learned earlier. Okay, so this is what happened here lah. Okay, what happened here is that in the first clock cycle, the processor get the instruction from memory and decode it. Means that on the first clock cycle, okay, the CPU will retrieve the instruction from the code memory, okay, and go, okay, and put it to the CPU in order to decode it. After it decoded, then after that, it in the next clock cycle, okay, what happened here? Then after that, it will execute and store the value on the data memory. Okay, so the von Neumann architecture is actually a relatively older architecture and was replaced by Harvard architecture. Okay, so in now, okay, all the computer systems are using Harvard architecture. So that's why you can do multitasking, you can do a pipelining, you can do simultaneous program or simultaneous data processing at the same time. Why? Because we use the Harvard architecture. Okay, so for the Harvard architecture, okay, so you have the CPU and then you see here the code memory and data memory are separated from one to another, okay, and it has its own buses or own pathway, okay, it not share the same pathway, okay. Since it's not share the same pathway, means that you can do pipelining or multitasking. Okay, so in this Harvard architecture, so processor can be complete an instruction in one cycle if appropriate pipelining strategy are implemented. Okay, so if you're going to execute the ADD instruction earlier, so you only need 1 clock cycle. Okay, compared to if you use the von Neumann, you need 2 clock cycles. Okay, so most of the modern computing architecture are based on Harvard architecture, but the number of stages in the pipeline varies from system to system. So you need to know how to differentiate between Harvard architecture and von Neumann architecture. Okay, so that one is for the architecture. Now we're going to see what are the organization. Okay, so what is organization? Okay, computer organization is typically referred to the operational unit of the system together with their interconnection, how features are implemented. Okay, so in this organization, it consists of hardware details that are transparent to programmer. Okay, so the programmer will know how many input output available, what are the size of RAM, what are the size of ROM, and what are the register, how many register available in that organization. Okay, in that computer organization. Okay, so many computer manufacturers offer a family of computer model, all with the same architecture, but with different in organization. Okay, so all the computer models, such as if you buy from the Acer, you buy the laptop from MSI, all use the same architecture, which is it use the Harvard architecture, but the organization are different from one model to another model. It depending on the laptop that you buy lah. Okay, some laptops that you buy, maybe it has a 3 USB input output, and the other laptop have one input output, and some of them have your USB 3.0, some of them have USB 2.0. So that is the organization, the way that the designer going to put to the computer is different. Okay, so the architecture may survive many years, but its organization changes with the changing technology. Okay, so let's look at how the organization changed from early 19 to now today's. Okay, so this is the computer in 90s looks like. Okay, now on the 20,000s, so this is the computers looks like, and 2010, this is how the computer looks like. Okay, so can you tell me, so what are the difference between the computer in 90s, 2000, and 2010? Somebody?
The color is changing.
Okay, the color changing. What you mean by the color? Is it the display of the monitor display?
The 90s is white color, 2000 is black, 2010 is hybrid.
Okay, so okay, so you focus on the color. Other than colors, what else? Okay, you can see here. Okay, the connection between the CPU and the what we call here keyboard. Okay, so this one here, you see this one here use the serial connector for the keyboard and mouse. But in 2000s, you see it used the USB connection, while 2010s now it is wireless. Okay, so this is how the organization changed from from time to time. Okay, and then you see this one use the floppy disk. Okay, you see that one. This one is use the floppy disk. Now on 2000, no more floppy disk. Okay, now it's changed to the what we call here. Maybe this is a CD or DVD player. And in 2010s, no more DVD, no more floppy disk, no more CD players, because now we use the USB flash drive, okay, to transfer a data. Okay, so in maybe like in 90s, okay, we it used the for the hard disk, maybe it used the HDD. Okay, but in 2000 and 2010, we use the SATA and we use the what we call it. Other than SATA, we have another hard disk called, I forgot the name. What is that?
SSD?
Yeah, SSD. Correct. Okay, now we use the SSD. No more the HDD. Okay. And then in terms of RAM, this one maybe it's use the SD RAM. Okay, now for the 2000, use the DDR2 or DDR3 RAM. But now 2010 is use the DDR4 SD RAM. Okay, so the organization is changing from year to year. Okay, for the CISC versus RISC, okay, this one you can read it by your own. Okay, now I'm going to focus on the introduction to AVR. Okay, any question up until here? Ada soalan tak? Okay, so if no question, so let's look at the introduction to AVR. So, okay, in the first two module is quite boring because it is more on the historical introduction, more on the theoretical part, but on the module, on the third module and onward, you will learn about the programming. Okay, so the AVR architecture was designed by two students. Okay, so this is a historical part. Okay, maybe you can read it by your own. Okay, there are many kind of AVR microcontroller with a different properties. Okay, we have a lot of AVR microcontroller out there. Okay, with different properties, with a different pin out, with a different ROM size, RAM size, and EEPROM size. Okay, except for AVR32, which is a 32-bit microcontroller, AVR are all 8-bit microprocessor. Okay, means that you can send 8-bit data at one time, except of AVR32. Okay, which is a 32-bit microcontroller. Okay, so Atmega 32 actually is a 8-bit microprocessor. Okay, so what happens when you have a larger data to be sent out or to be sent out from CPU to output or to read from input to CPU? Okay, if you have a data larger than 8 bits, what you're going to do is the data will be broken into 8-bit pieces lah. Okay, to be processed by CPU. Okay, if you have a 16-bit data, you need to broken it to 8-bit and 8-bit by 8-bit. So you have two 8-bit data. If you have 32-bit data, you need to broken it to 4 8-bit chunks. Okay, so the AVR is a modified Harvard architecture machine where program and data is stored in separate physical memory systems that appear in the different address space, but having the ability to read the data item from program memory using the special instructions. Okay, so let's look at the AVR family overview. Okay, so AVR actually can be divided into 4 groups. Okay, so first one here, we look at the classic AVR. Okay, every time you see the 8090S XXX means that this one belong to classic AVR. Okay, so this is the original AVR chip. Okay, okay, for the classic AVR, there are 3 models here. Okay, one is a 2313, 2323, and 4433. Okay, so the size of ROM, RAM, EEPROM, and input-output pin are vary from one model to another model. Okay, so this is for the classic AVR. And then we have a Mega AVR, which is Atmega XXXX. Okay, so this Mega AVR actually is a powerful microcontroller with more than 120 instructions. Okay, so this is the instruction lah. Okay, that you're going to use. Okay, for the Atmega 32. Okay, so this Mega family has a lot different peripheral capabilities which can be used in different design. Okay, so this is the model of Mega family. We have a Mega 8, Atmega 16, Atmega 32, 64, 12, 80. Okay, so now we're going to focus on Atmega 32. Okay, so you see here, the size of ROM for Atmega 32 is 32 kilobyte, Okay, RAM size is 2 kilobyte, EEPROM 1 kilobyte. Input output pin out ada 32. We have 8 analog to digital converter, 3 timers. Okay, and then these are pin numbers and packages. Okay, so the size of what we call here, the size of ROM, RAM, EEPROM, and input output pin, okay, is vary from one model to another model. Okay, then we have a tiny AVR. So this tiny AVR, every time you see the add tiny means that it belongs to tiny AVR. So has less interaction and smaller package compared to Mega family. Okay, can design system with a low cost and power consumption using tiny AVR. Okay, if you're going to design a certain system that require less power consumption with a low cost and then the number of sensors that you're going to integrate is limited. Okay, so you can use the tiny AVR. Okay, similar to Arduino lah. Okay, for Arduino you have an Arduino Mega. Okay, and then you have Arduino Uno. Okay, so the tiny AVR actually is similar to Arduino Uno. Okay, so this is the part number. Okay, the size of ROM RAM and I/O pin outs. Okay, so the maximum number of I/O is for the tiny is 12 lah. Okay, you can connect it to 12 sensors. Okay, maximums. Okay, and then it have a ADCs and timer as well. And last but not least is a special purpose AVR. Okay, so the IC of this group can be considered as a subset of other groups, but okay, it has the special abilities okay, made for the designing specific applications, such as if you're going to use the USB controller, you can use this special purpose AVR. If you are going to use a CAN controller or LCD controller, or you're going to integrate your system with Bluetooth or Zigbee, Ethernet controller, FPGA, you can use this special purpose AVR, because this special purpose AVR has the special capabilities dekat sini. Okay, you can see here. This is the special capabilities for each of the models. Okay, so how to get familiar with the AVR part numbers? So AT here stand for the company names. Okay, the Atmel. Okay, and then followed by the Mega Tiny 90S. Okay, so this one belong to your family. Okay. And then 1 to 8. Okay, so for the Mega 1 to 8 represent the size of your ROM. Okay. So this one, okay, AT Atmel Tiny is belong to Tiny group, Tiny family, and the size of ROM is 4K. Okay, no need to remember this thing lah. Okay. Okay, in terms of Atmega 32 pin out, okay, this is important. Okay, in order to write a program, okay, you need to know the hardware architecture. Okay, so Atmega 32 pin out, okay, you need to know the Atmega 32 pin out. For Atmega 32, we have 40 pin out. Kita ada 40 pin out. Okay, okay, so this is started from pin number 1 until pin number 40. Okay, so since okay earlier, okay, how many input output available for Atmega 32? Ada berapa input output Atmega 32? We can see here. You have a 32. Okay, a total of 32 input output ports. So Atmega 32, you can see you have port A, port B, C, and D. So this is your input output port. Okay, each of the port here have 8 bits. So 8 plus 8 plus 8 and plus 8, you will have a total of 32 input output port. Okay, what about the rest? Another 8 bit. Okay, the rest of 8 bit, okay, used for the reset. Okay, pin number 9, VCC. Okay, so this one here, okay, you're going to clear all the register and restart the execution of program. You can put connect this one to switches, okay, to do the reset. And then you have the VCC. Okay, so this VCC provides supply voltage to the chip. Okay, so you need to connect this VCC to 5 volt. Okay, make sure no more than 5 volt. If not, the chip will burn out. Okay, then ground, you need to connect it to ground lah. Okay, then we have the external 1 and external 2. So these pins are used to connect it to external crystal for clock source. Okay, so in order to increase the processor, you can connect this external 1 and external 2 to your clock source crystal. And then we have the AREF. Okay, so every time you're going to do the analog to digital converter, we need to have the A reference, okay, the voltage reference. Okay, later you will learn about how to determine the voltage reference here. Okay, so this is a reference voltage for ADC, and then AVCC. AVCC is a supply voltage for ADC and port A. Okay, you can see port A, instead of using it as a input-output port, it also can be used as the analog to digital converter. Okay, each of these port here, if you can see the port B, port D, and port C also have the others features. Okay, others features. Instead of using it as an input-output, it can also be used as other features. Okay, and then all right. So next, after that, okay. Okay, so I think we continue this one in the next class. Okay, which is each of the I/O port pin and their function and how to initialize the input-output pin. Okay, any question up until here? Ada soalan tak?
Doctor, I have a question, but from something from earlier. For the assembly language, do we have to take into account whether it's a native assembly or cross assembly when we're writing the code?
No need to take. No need to consider that, because nowadays all of the assembler are native assembler. Means that you write the program in one computer and at the same time you can process it.
Okay, thank you.
Okay, other than that, any question?
Actually, I have another question. For the IC that you just showed us, you said that we're connecting the clock source to an external crystal. What is meant by an external crystal?
Okay, so for example, okay,